Okay, so good morning to you all. I'm Mike Mead. I'm one of the Meltio leads for the UK. I'm just going to give you a quick walkthrough of some of the features on the presentation, and then I'm going to give you a bit more of a live demo by going into the machine and seeing if I can show you some of the things that are happening there. We're going to try and switch platforms midway through, so you have to bear with me in the middle, but all should run pretty smoothly. So, can everybody see the slides, just for a start?
Yeah.
Okay, and you've all got good quality audio, you can hear me okay?
Yeah.
That sounds clear.
So, the Meltio system is a laser metal deposition system. So what we're doing is we're producing solid metal parts using wire or powder. Mainly we go with wire. Because of its easy handling, less health and safety, etc., etc. But it also gives us much better parts at the moment. You'll see on the back of this slide, it's quite a handy title slide, but it gives us a lot of explanations about the piece as well. So that is the Meltio printhead that you can see at the back. You'll see each of those white cables coming down with the L numbers on them. They are the lasers. And integrated into those lasers is a thermistor. So we've got full temperature monitoring and there's 6 of them. So it's a 6 laser system that projects 6 lasers down. And what we're looking for is an overlap in those lasers to form a kind of Venn diagram at the bottom. And then we feed our metal wire into that to produce our parts, which I'll show you later on. Meltio is about producing near net shape parts. So we're not producing the fancy lattice geometries. We're producing affordable metal parts that are functional parts that we can then machine back afterwards. So we're going near net shape and reducing the parts that we can see, reducing the time taken in other processes. As you can see, we're looking for this shift from the niche industrial applications of powder into more functional parts. So you can see on the left there, we've got the fancy lattice work, the powders, the high print times, high cost parts. And what we're looking for is to change that mindset. And if we can do that, then we can, as I say, produce these parts at much lower cost for much more practical reasons. Meltio system fits in at a lot of different stages of the part. We can look at the research, which is part of my job, and I work with a lot of the technology centers and the universities, but we can work right through that life cycle. And I know this is, it feels a bit sales pitchy for a techie to be doing, but I really do see it fitting into a lot of the different areas. So this is some examples, and I've got most of these parts here. I've not got the engine mount, but I can show you the others. We're looking at very quick print times for very dense, solid parts to reduce our machining afterwards. So if you see the mold core in the middle there, it's nearly a 7 kilo part, 6.5 kilos, just over 23 hours print time at a cost of €76. The knee implant, which is the TI-64 titanium piece in the bottom right-hand corner. I was speaking to a company at the show last week before. They sell that part for €15,000. We're making it for 50, which is absolutely crazy. So that's just giving you a flavour of some of the parts, which I'll show you say live in a moment. The Meltio system is an open material platform. So if you can get it in a 1mm wire, then you can put it through the system. So at the moment, you can see here, we've got various grades of stainless steel. Titanium TI-64. I'm at the process of working on TI-5553 at the moment. We've got Inconel, we've got carbon steels, and under development are copper and aluminium. The release dates for those are expected end of 2021. I'm going to say that they're not going to be ready for that. They're going to be pushed back, particularly the aluminium, just because of the difficulty of getting it to stack. Multi-laser head deposition. So basically what it means is it can do multi-wire. So we've got 2 feed heads in the system, and we can mix the 2 wires together. So we could go for, say, let's say we've got the copper working, copper for thermal conductivity or heat conductivity, and then we could have an Inconel outer shell for heat distribution. Sorry, for hard wearing. So this multi-metal concept is something that's quite unique to the market. There's nobody else doing multi-metals at all in the system. The print head I showed you is the same print head, but we can deploy it in 3 different methods. And this is, again, something that is quite unique to Meltio. Because we're doing an argon shield, not a full argon build chamber, we can deploy the system in quite novel ways. So you can see there that we've got the M450, which is the standalone 3D printer on the left-hand side. We've also got the CNC integration in the middle. So the Meltio head sits as a depositing tool alongside the CNC spindle, and we can come down, do a little bit of printing, machine, print, machine, print, machine. So we can go back and forward, which gives us the ability to get to lots of different geometries. Then you got the engine robotic system. So the robotic system is probably the most free in terms of the geometries, because we've got the 6-axis of the robot plus 2 axes of a turntable if you add that. And because we're using wire rather than powder, we can rotate off an axis. So that print head, we've been testing up to 45 degrees at the moment, but I suspect it can go much further as well, as I say, because we're only feeding wire into a melt pool. I'll give you a couple of minutes just to look at that. There's no real need for me to go through all the stats. They're available as data sheets if anybody is really interested later. So that's the M450. And then that's the control system for the engine. So it sits alongside the CNC or robot development. Can you see the videos okay, Jordan? I'm just going to go, this is the robot engine. So this is a 40-hour print, 8 for the central spool, and then the remaining 32 comes from...
Videos fine, Mike.
Okay, thank you. So that piece is about maybe 3.5 feet in diameter. Just run that again, just a quick video. But you can see this metal deposition happening. You can see the various angles that we're printing at. So we're keeping the print head normal to the surface in this state. We are printing these hollow propeller blades as we come through. Oops, sorry. Didn't mean to go again. And here we can look at an overhang test. So you can see the system working in a slightly different way. So we can either work on the rotational system or we can rotate the head. So the geometries that we're getting are quite unique. You couldn't produce most of these on a powder system at that price. Okay, so back just to looking at some of the parts, and I'm going to just try and change over now, stop sharing my screen on this one, and change over to a camera on the other system, and hopefully we'll be able to get everything working. I can take you into the machine and give you an actual live demo of this. Will be the M450. Not going to be the engine version. Jordan, I'm just going to need you to be able to tell me that you can see me on screen, or at least see me.
All good, Mike. Can see you there and hear you.
The other one. Okay, so this is the M450, the standalone one. Sorry if I give you a bit of a Blair Witch Project type movement here. I'm going to try and just pin myself to the screen. Okay, so as I said to you earlier, the 6 laser system. So we've got each of these lasers. These are the ones without the thermistors built in. So these are an older set, but all the new ones come with an integrated thermistor, which allows us to do full unmanned running of the system, because we're monitoring all the temperature, we're monitoring the melt pool, and keeping a constant flow over everything. So when the system came out, it was kind of limited to a person being here. We're now getting to a point where, whilst we recommend some monitoring, we don't have to be here all the time. We don't have to stand here and watch the whole thing running. So let me see if I can show you all of these lasers running. So we've got a projection of 6 lasers. You can see those on the back of my hand. As I bring my hand up, what happens here is those lasers start to overlap, and we can feed our wire into the system, and that gives us our melt pool. It's what gives us the heat to melt the parts. Under here, we've got our argon shield. So we're feeding our wire through the nozzle here, and the argon is down and forms a sort of vortex around it. And what that gives us is the ability to go from pressing print to starting print really quickly, about 60 seconds. The comparative EOS type systems, the powder bed systems, you're looking at sort of 4 to 8 hours to fill the whole chamber. We're not filling the chamber, we're isolating the part as you would do with a welding process. Webcam up here in the corner, which gives us full monitoring and a time lapse of the print. And then we've got a touch off arm that'll come down here. That arm will touch off on either the substrate, which we've got down here, or onto an existing build plate or a billet or whatever you have printed, so that we can find our datum and then continue printing upwards from there. Advantage to that is that we can use the system for repair, but also that we can use the system just to print features. So there's no point printing a whole billet and taking bits back if we don't need to. We could just print add-on features to an existing machine component, which will give us the most effective and the most efficient way of working our system. As I said earlier, this print head can be deployed in the CNC or on the robot. It's the same technology. The only thing missing is the touch-off arm. And when we're using the CNC or the robot, we have a load cell built in at the back of the print head, and that's what gives us our read through. Other features, so we've got just a wire feed down here. The wire feed here is just standard MIG welding wire, and that makes the part to produce really cheap. So if you're looking at, say, the desktop metal system, you're looking around $500, I'll work in dollars, $500 a kilo for the metal for that. For this, you're looking around $5 a kilo. It's cheaper for us to buy the metal for this than it is for us to buy plastics for our plastic printers, which is just a bit of a crazy stat, really. So let's see if I can show you some parts. As I said earlier, we're not looking at hiding the layer lines. We keep our layers in, we're producing near net shape, but what we do have is the ability to just machine back. So we've taken 0.5 millimeter off the surface of this. And because of the way that we structure the melt pool, you get extremely high density parts. So we're looking at somewhere around 99.678% in there. All the test data is comparable to billet, but what we're seeing is that because we've produced the metal wire first, and then we are laser treating that, each time we do that, we are refining the microstructure. So we're getting a much tighter crystalline structure on the surface of the part, which gives us obviously a higher strength, tighter part. And we have all the data sheets for, at the moment, for TI-64, for various grades of stainless, and the Inconel 718. Here again, you can see this is the glass molding one that I spoke of earlier. You can see the layer lines in there. I'm not hiding anything, but then taking just over 0.5 millimeter off, you can see we've got this machine part. Now, if you were to produce that from billet, there are a significant amount of cutting processes in there to get you to that stage. Inconel 718, again, we've left the base so that we can see these layer lines, but it's quite hard to show you guys all the reflections on here. This is the fan blade. that you can see on there. Multi-material parts. So we've got a tool steel here combined with a stainless. And if anybody else can tell me a way of combining parts like this, I'd love to hear it. Honest answer, do we know what the metallurgy is like in this process for bonding at the moment? Yes and no. So it's under trial and under test to see how different materials bond to each other. If you can weld them together, then you'd expect that this process is the same, but we don't know. So if we had, as I said earlier, copper and Inconel together, what's the thermal expansion like? How do they hold up against each other? You know, what's the process? So that's something that we're working with our technology centres and universities to work on. But as I say, it's a bit of an unknown at the moment. This is a titanium TI-64 watch bezel made for a company that make phones and watches and have the same name as a fruit. I'll let you guys figure it out from there. You can see this is the raw version. This is just off the machine. And then this is the finished. Probably my favorite one to show because it's the only one that I don't have to look around. It's the smallest one. Sorry about the focusing. There you go. So hopefully that gives you a good flavour of the Meltio system and the process by which we operate and some of the parts. Can I take any questions from anybody or show anybody anything again in more detail?
What's the sort of maximum size you can work to for components?
On the M450, we're 190 millimeters by 200 millimeters by 450 millimeters, hence M450. The only thing you have to take off from the height is the height of your substrate. On the engine, it's limited to the size of the robot or CNC. So for the robot we've had running in Spain at the moment, the biggest part we've just done is a fan blade part, which is a hollow structure, but it's 1.7 meters tall. Quite large. Any more?
Yeah, I mean, is there any way of refining that if we say wanted a part that was some machining but not having to machine it all over, is there any way of refining that surface finish, or is that kind of as good as it gets?
I would say that's probably as good as it gets, to be honest. I can get the R numbers from the testing
yeah,
for the surfaces, if that helps you guys. I don't have it to hand at the moment, but I know we've had the studies done.
Yes, that would be interesting actually to see what that actually looks like.
I mean, the other thing is quite often we've done some work with Rolls-Royce, and we were talking about significantly over-engineered components that were actually, we would only need to machine the mating faces. There's no need for a lot of the others to be done. Obviously, that's part of the aesthetic of pieces, and in some instances, functionality for wind resistance and that kind of stuff. So.
Yes, sometimes quite a few of the parts we've had done in metallic have been in the airflow, so we've had to have a reasonable surface finish. I mean, it's not always a machine finish. Sometimes we've accepted the kind of as supplied DMLS finish, but I would say that's a bit better than what I can see. But it obviously depends on the application. We're working on quite a range of different parts, I would say.
Absolutely, and Meltio is what I would say is application specific. So it's not going to be for everything. If your part is a 90 kilo part, then there's going to be other methods of manufacture that are more suitable. The same for if you've got something with a super fine detail, or a massive, lattice 6-axis geometry. It's the same as anything else. It's using the right tools to get to the right end goal. And Meltio is just another tool in the cycle. Granted, it's a much cheaper way of doing other things, but that doesn't mean we should put everything through
And do you have sort of design guidelines on kind of overhangs and those sort of things that you could give us?
Yeah, I've got a design guideline sheet that Catherine can share with you guys after the call. Have you guys seen anything like this before? You know, you guys will see a lot of stuff happening in the market. I'd love to take your feedback on it as well.
I've heard about that sort of thing. That's the first time I've actually seen a kind of a proper demo and actual parts of it, I must admit.
Seen something similar without lasers at Warwick University.
So that would be the WAM system. So WAM is probably the closest thing to this, I would say. But it uses an arc. It's a true arc welding process. It's much faster, let's be honest. WAM is faster. But the feature size for a WAM part, you're looking at maybe a minimum feature of 4 to 6 millimeters. With this, we're down around, well, we're at 1 millimeter. Our bead width is 1 millimeter by 1. So we can get a much finer detail size. We're also a much cleaner process. So it's, you know, you don't get the splatter that you do from WAM. And we're also better density.
I was going to say, the propeller video looked very impressive. Like the finished surface of that seemed maybe better than the parts you showed. Is that just because it's larger so you don't see?
Yeah, and I also don't feel like the video captures the surface truly, if that makes sense.
Yeah, yeah.
I was giving you a very close-up view of some of the parts here. So yeah, it is good, but it's comparable to what I showed you on the video.
It was impressive using the robot and moving the component. That was very impressive.
Yeah, it is. It's a very nice way of being able to mix the two axes together. And as I say, it gives us the ability to produce very difficult geometries. I've got a couple more videos if you guys want to see them. The time is yours, really. It's up to you guys.
Yeah, okay.
Yeah, okay. Just give me 1 second then, and I will load one up for you. So I can show you the fan blade video. And we've got quite a good one as well that is like a twisted pipe. It's a very quick video, but it gives you a good feel for how the Meltio system works and how the robot works as well. Hopefully, if I share the screen now. No, it's not doing that. You guys see this?
Yeah, all good, Mike.
Yeah.
Brilliant. So this is the fan blade. You can see it's a hollow structure. It's an entirely open structure. Bead width is just over 1 millimeter. But we're using the full height of the robot, keeping the head normal to the surface. And it should pull out and show you that this is quite a tall part. So you can see that full structure. That is built onto a 50 millimeter substrate. You can see that one. Skip through. This is a ribbed tank. So you can see here, we're staying normal to the surface again, rotating on the base and coming out, and then again, coming back in. So we've got this ribbed surface and rotating back around. final one I've got for you guys is this pipe. So again, these are quite difficult structures to manufacture traditionally.
Mm.
As a sort of expert, I can see that there's a little bit of calibration he's doing on this machine, because you're getting these kind of like tails on the left-hand side of the model as it comes around, just slightly out of calibration. That's the only bit. One of the lasers is out of the line of the Venn diagram. You get this tail on the print. And that's me, unless anybody's got any interrogation that they want to put forward. I'm more than happy to answer as many questions as I can. I can't believe nobody's got the price. Everybody asks the price question.
Thanks for going through all that. The videos are very interesting.
Pleasure, no problem at all.
Is there any chance of sending us a little demo piece that we could have a look at the sort of physically in our hands at all? It doesn't have to be anything any big.
Yeah, sure. I can do we can just for you, send them through.
Cool.
Okay, brilliant. So it'll be from Catherine that will follow up with you guys.
Mm-hmm.
Any technical questions will come from me, I can pick them up. But other than that, that's it from me.
Brilliant. Thanks very much. That was really good.
Yes.
Thank you.
Thank
Thank
you.
you all for joining.
Thank you.
Thanks, guys.
Thank you.